Hey everybody, and welcome back to Calc 3 online. I wanted to start off today and kind of just build off of what we did with vector lines last class. So we had a problem at one point, actually I think it was the very first thing we did, where I had x equals 2, and I said let's think about what that is in R, in R2, and in R3. And now that we saw this normal form equation of a line last time, really we can kind of take this and do the same thing that we did with that x equals 2. So probably not that surprising, but one of the benefits of vectors, because they build so naturally where you just tack on another component, it translates really well back to that original idea with the x equals 2 kind of problem. So if we think of the vector equation in normal form like this in R, that's where we're going to actually just get a point. And this is exactly the one we saw last time. So in R2, that would be understood as a line. And this thing in R3, this is supposed to say, that's a 3 right there. It would be a plane. And this would really keep extending too. Like if you wanted to, you could go further. But really, like, the nice part about vectors is that the only thing that changes from here to here to here, right, is how many components there are in these vectors. But the computation is always the same. You just do these dot products. P is a point on the, well, in the point, or on the line, or on the plane. X is always your variable vector, right? So here it's just like x, right? Here it's xy, and here it's xyz, and these ends are always the normal vectors. So I wanted to kind of go through an example where we would actually create the equation of a plane using this form. So we have a point and we have a normal vector. And I'm going to link this back to some algebra also to kind of show you how we would do it in like an algebra 2, although I feel like I don't really do this too much in algebra 2, but this is not a plane, right? This is just a point slope for a line. But I'm going to show you a connection between what we do here and how to do it with some algebra without vectors. But doing it with vectors is really quick. So, I mean, you got 2, 3, 4, a normal vector, right? I'm going to put another 2, 3, 4 over here. And I'm going to dot it with x, y, z because we're in 3D, right? And the point is 2, 4, negative 1. And literally, if you just go and do these two dot products out, you'll have the answer. So you get 2x plus 3y plus 4z. And that's going to equal, let's see. Oh, mental math. 4, I'm just going to do it out. Plus 12 minus 4, so we get 2x plus 3y plus 4z equals 16 minus 4 is 12. So this is a plane that, you know, you should recognize that from algebra, I guess algebra 2. But we just did it with dot products, and I can kind of show you a way to do that with a kind of a more algebra 2 method, I guess we'll call it. So just like we have this point slope form, right, where there's kind of a structure of a difference between these x's and y's, and then a scalar, you can sort of always set up a linear kind of structure that way. So I'm going to put all these letters down, and I'll explain this here. Equals 0. So if I had moved this part, right, over to the other side, I would have had it equal 0. So in a sense, I'm just kind of setting everything on one side, and I know that a linear kind of thing, whether it's a line or a plane or a hyperplane or something like that, it's going to have a difference between the variables like that, right? These x, y, and z should stay. This, and this will be a point. And then I know that these a, b's, and c's are going to be linked to the normal vector, which is really just because of how... Hey everybody, sorry, someone just came into my room before, so I lost my place, and I don't quite remember what I was saying, so I'm just going to start over here. So this right here is like the general kind of structure for any linear kind of thing, like a line or a plane. And I mean, this one is specifically a plane because there's 3. But if you keep adding on more terms like that, you would get the higher dimension version of whatever that structure is. And just to kind of show you how we could get this, okay, we know like in point slope, right, x1 and y1 are from the point, and this relates to the slope, which is like actually when we write it out like this, it actually is the normal vector. So if we go and fill this stuff in, the normal vector 2, 3, 4, and then we have x minus 2, and then we have y minus 4, and then we have z plus 1. That's how double negatives work. And actually, if you go and multiply this out and simplify it, right, you're going to have 2x minus 4. You're going to have 3y minus 12. You're going to have 4z plus 4. And if you look, so if you add 4 over, add 12 over, and subtract 4, that's exactly what we got right here. It's not a coincidence. This is 12. You're going to get the exact same thing either way. And this kind of leads to sort of a shortcut that we can use. So if I ever had, if I have a plane equation, 7x minus z, I'm going to write it a little bit, I'll do a plus there. So that I'm just doing to stress that there's no y in there, right? So this is a plane. There are infinite amount of normals to a plane, right? Because if I, just draw this, I could have this normal, but then this could be a different vector because it's bigger, and that could be different because it's bigger. So all of these are normal vectors, but a shortcut to get a normal vector would always just be to pull off those coefficients if it's in this kind of form. So a normal here would be 7, 0, negative 1. And that'll be important for stuff later on, like being able to like pull out a normal like that. It could, you'll see, there's a lot of times where it's going to be helpful, but it kind of goes back to knowing how to like get this structure up here. So I wanted to also talk about the kind of vector form of a plane. And this was the vector form for a line. And just to kind of recap this is your variable vector, this is a point on the line, and this is the direction of that line being scaled, right? And this scalar coming from all of the real numbers lets you go like in one direction, maybe that's the positive scalar, and then you flip it and that goes in the negative. So if you think of a plane, in order to create a plane, right, you would need to go and scale like in one direction, but also this other direction. And if you do that, you will be able to craft the entire plane. So there are going to be 2 variables that are needed to scale to get a plane, basically. So with that in mind, you can sort of begin to see why a plane equation for vector form, it still needs a point, right? Like if I kind of make this a little more visible back here, you know, in a sense, that point right there is this point, and then I add to it like some scalar, I'm going to call it S, on a direction vector. I'm going to call it D1, and then I'm going to add to that T times, that's my scalar T, another direction vector, so maybe this one. And there's, you know, extensions of this. So this is definitely the equation of a plane. But if I should probably, I think it's in white, so it's hard to see. But these have little arrows on them. So if I extend this one more time, right, you basically just get the higher dimension version. We could call it a hyperplane. A lot of higher dimensional objects, we just throw the word hyper in front of it. But it really is, you know, just we went from here, a line, to a plane, to the next version up, and it basically, you know, it's like, here's a line, and a plane involves these two, you know, direction vectors, and then we can kind of create a plane, right? And if you go one more dimension up, right, you like scale one vector, scale another, there you have a plane, and then you scale like maybe up in Z, and so you got kind of this 3D structure. And so I'm not a very good artist, but I will attempt this. But basically you create a box. You create a hyperplane is like a 3D shape in embedded inside of four-dimensional space. So this guy is basically like a R3 box, we'll call it, living in four-dimensional space. And those are actually useful in the kind of math that I studied in grad school. We worked in four-dimensional space a lot, and there's a lot of evidence that shows that the universe we live in is kind of related to this sort of structure and ends up basically being more useful than you maybe first think. And it's kind of fun to think about that stuff too. So to kind of just end here, I wanted to do a few problems that just show how we might write the equations of specific planes. So I want to make sure that you can do the vector, the standard, and we haven't done one yet, but we did this for lines and it's very similar, the parametric equations for a plane. Personally, I think the vector form is one of the easier ones. And I think over here there was a Q that got cut off, I realize now. So the points are P, Q, and R. And to do the vector form, right, we could take any of those points. So maybe I'll write again here. The vector form is just this one. And so the point vector could really be P, Q, or R. It doesn't matter which one you take. And then to do the direction vectors, you just need to do subtraction, because if you want, you could say D1 just equals P to Q, right? So we're going to do Q minus P. So 1 minus 1 is 0, 0 minus 1 is negative 1, and 1 minus 0 is 1. And then you need a second direction vector. We could do, you have choices here, but we could do like Q to R. So we could do R minus Q. So 0 minus 1 is negative 1, 1 minus 0 is 1, and 1 minus 1 is 0. And so now you have all your parts. So, you know, in terms of doing vector form, all you got to do is subtraction, and then you just put things in the right spot. So we have you can use 1, 1, 0. You don't have to. You could use 1, 0, 1 there, but I'll just use that. And then you do need that s that represents the scalar, right? And then you have 0, negative 1, 1, and then you have negative 1, 1, 0. And that is a perfectly good, vector form right there. And parametric is probably easiest one to do now, because once you have the vector, you just pull everything off. So your x would equal 1 plus no s, right? Because 0 times s right there, and then minus 1 t. Y would be 1 minus s plus t. And z would equal, let's see, s, just s. This is the parametric one, and these, again, are very useful if you get into programming. So a lot of computers want to define the variable in terms of these parameters, s and t, and really, it's not too bad if you know how to write it with vector form. Then you can just pull in the parametric out of that. So to do the normal form, right, that's the, what color have I not used here? I guess I called it standard, but it's really the normal form. That's the n times p, or I think actually the order I did was nx equals n dot p. We know x, we know p, but to get the normal, you kind of just need to craft it, I guess is how I would say it. So I'm going to draw a picture here. I want to draw a picture because I want to kind of show you. So if you have some normal vector, okay, that normal vector, I don't have a lot of colors here. I'm running out of colors, but that's okay. Maybe this is my direction vector. Those two have to be perpendicular, right? So if you have a direction vector, right, which we do, we could take negative 1, 1, 0, right, which was direction vector 2, just from above. And if I dot that with something to make them equal 0, 0, 0, then I know they're perpendicular, because that's like our one of our tests, I guess you could say, to figure out if vectors are perpendicular. So there's lots of options here. I mean, you could kind of just guess and check. One that I'm just seeing right off the bat, if I do 1, 1, 1, right? That's negative 1 plus 1 plus 0, right, is the dot product on that. So 0, 0, 0. Oh wait, sorry. Dot products are not vectors. I knew that looked funny. So equals 0. That would mean that I could take this purple vector, 1, 1, 1, as my normal, and then now I can just go and do 1, 1, 1, that's n, dotted with x, y, z, and then equals, I'm going to do the point, I'll just do p, 1, 1, 0, and then I'm going to put my normal vector in. Whoops, not in. 1, 1, 1. And so that is just plugging into here, right? N, 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 X, X, P, P, just from that P. And then if you go and multiply that out, if I did this right in my head, I would get x plus y plus z equals 2. So that is kind of your standard or normal form of the plane. This one is, this is your vector form, and this is your parametric. All of these three things really say the exact same thing. So one quick thing that I want you kind of to realize is if you start to see these normal vectors when you look at planes in kind of the algebra 2 way, it should be easy to kind of just spot whether they're parallel, perpendicular, or neither. So, the normal vector here, you just pull off the coefficients, 1, 4, -3. I'm going to call that n1. The normal vector here would just be -3, 6, 7. And if they're parallel, in vector world, that just means that, some vector 1 needs to equal some scalar of vector 2, right? Because, here's a vector. If you're, double it, your other one's double it, then those two vectors are going to be parallel, right? If you're perpendicular, right, then you could always just do, that could be tested with V1 dotted with V2 and see, is it equal to 0? And in this problem, if you do it out, if you do N1 dotted with N2, you can see that they would be equal to 0. So that means, I'm going to attempt to draw this. If this is one plane I have here, I'm just going to say that's that plane. I know that the normal vector of this plane is basically in line with the acting as a direction vector to the other plane. So I am not a great artist, but I'm going to attempt it something like that. So this blue vector is basically acting as a direction vector to the purple one, but it's perpendicular to the green one. And the yellow vector here is perpendicular to purple, but in line with acting as a direction vector for green. So I want to do one more problem. So this problem just kind of brings in something we haven't seen in a few days, and it's good to kind of not forget about it. So I give you a plane equation here and a line in parametric, okay? And I'm asking, do they intersect? And if they do, hint, hint, then find the angle of intersection. And this is just kind of a good problem to show you how to find angles of intersection, how to even test to see if they're going to intersect, that kind of thing. So the way I would think about determining whether or not they intersect is actually kind of similar to this problem over here, right? So say the yellow is like the line, okay? It's going through this purple plane right here. If they intersect, right, the two vectors, the normal for the plane and the line, their dot product basically couldn't be 0. It might be easier to actually draw this over here. So let's take a plane and let's assume the line up here in 3D space didn't intersect the plane. So if you take the normal coming out of the plane, the only way this is going to happen is if they didn't intersect would be if the direction vector for the line and the normal here to the plane were perpendicular. As soon as you tilt this line in 3D space a little bit, so it's going to intersect maybe down here or something, then this angle of intersection between the normal in blue and the direction vector on the now slanted line, right, are non-zero. The dot product of them is non-zero. So long story short, if you take the normal to the plane, 1, 1, 2, and you look at, so this is the normal, and you dot it with the direction vector from the line, which you can just pull out from each parametric, right? So you can get a 1, a -2, and a 1. 1, -2, 1. Right? That's the direction vector for the line. And you look at those, you see that n.d is, well, most importantly, it's non-zero if you calculate that out. That means they intersect. And so now to get the angle between them, right, you would need to go back to this kind of cosine formula that we've used before. So, u dot v, magnitude u, magnitude v, and basically we just plug in stuff on the right and take inverse cosine, and we will have the angle between them. So the question becomes, what two vectors u and v do I want to use? So if I draw another plane here, just say that's my plane. If I take u to be some direction vector in the plane, and my line is coming through the plane, there's going to be some direction vector for that line, which we already really have. That, again, is right up here, 1, -2, 1. We can really just dot those, just use those as like my u's and v's in this formula here, and we can get the angle that way. So really the only thing we don't have is like this yellow vector right here. But since it's a direction vector for the plane, it has to be perpendicular to the normal vector, which we have, right? So we can just be like, okay, what is some vector where when we dot it, when we dot it with, like, what is the vector that we dot that with and get 0? And if you just you can always do the thing where you put like 1, 1, and like x or z, whatever, maybe we should use z there. If you put in like a variable and solve this out, you can always solve for some vector that would then be perpendicular. So if you do that one, you would get that a direction vector for the plane is 1, 1, -1. And so now you actually have all the parts. We've got, this direction vector for the line, this direction vector for the plane. And so we can just go and plug those in to this cosine angle between vectors kind of formula and have calculate out the angle. So I'm going to kind of just cruise through this part here. So if we dot the two direction vectors, we get -2. And then the magnitudes are going to be √3 and √6. And so if you take inverse cosine of that, I'm doing my calculator, you get about 61.9 degrees. And that would be it.